Hello my friends of Untitled Water. This time we are going to make a tutorial on seawater intrusion modeling with MODFLOW-SWI2. So this software is updated version of Seawater for MODFLOW 2005. And it can handle the variable density modeling. In this time, we are going to process a coastal aquifer that is deeply stressed by pumping due to industrialization or heavy or agriculture on heavy with heavy intensity. Okay, so on the repository of this tutorial, that is, let me show you, GitHub. On GitHub, you look for Saul Montoya, that's my name. On Saul Montoya. No, on Saul Montoya, yes, on Saul Montoya. And then on repositories, as well on the link on this video, you will have this link. You will have these files. These are the MODFLOW files where we are handling with the SUPE Valley, and the model version is 4C. So you have to download everything. It's not so heavy. Okay, and then you can open with ModelMuse. So then we open with ModelMuse. We look for ModelMuse. Okay, so here is the address where we have stored our seawater intrusion, and this is the model of SUPE4C, the one that you are going to download from the web. This is already a constructed model, and the main purpose of this tutorial is just to introduce you to the modeling of this type of aquifers, and which is the spatial vertical crystallization. So I am planning on having a whole webinar on how to build this type of models. So if you are interested in doing this, please, and I really appreciate your interaction, please send me an email. This is my email, and we can, if 6 people are interested, I can actually get a webinar where we construct it and put it everything from the ground up. Okay, so this is the model. The model is on a coastal aquifer in Peru, it's in the Supe Valley, and we have here the agricultural part, and this part where there is not irrigated is not considered as an aquifer. In fact, it's a fractured aquifer, but since in this part there is no rain and all the rain comes from the highlands, is not interested as well on the groundwater flow. So if we are going to see it on the show active age, is not active. Yeah, it's part of the hydrogeological conceptualization that we have taken for this. The model aquifer is 90 meters, so we can, it's 100 meters this time. Yeah, it's almost 100 meters thickness and is divided in 2 layers. MODFLOW-SWI2 can handle this saltwater freshwater interface on the layer, so in fact there is no such need on defining many layers if you are working with Seawater 2. However, if you are dealing with if you want to put some more focus on the vertical heterogeneity or anisotropy, I would recommend you to use maybe 3 or 4. You will see which are the limits on this while working with MODFLOW with this Seawater Intrusion package, because like you will have an interface for each layer, and sometimes those interfaces are not quite exact. Okay, cool. Which is the horizontal discretization is 200 times 200, so each cell is around 200 times 200, and another question is, will this be enough for handling the data, or for simulating the seawater intrusion? I think that this is a tutorial model, so this is a model that is based on run well, that you can see, and then you can manage the output data. I think it's okay. From my personal perspective, I think if you wanted to do it like a more scientific way or more commercial way, like you will need to define a higher spatial resolution here, like maybe 50 by 50, and in order to define better like the seawater, the intrusion problems and the pumping effects, yeah, why not? This could be a good approach. And the problem will be that it will require more time to process, it will be more unstable, you will have more crashes, and like the output data will be also bigger as well. So for this tutorial we use just 200 by 200, use 50 by 50. Some cases like you will do 20 by 20, but I don't think that you will be dealing with 2 by 2 grids. I think that's impossible. Okay, well, cool. So what else should we do? Should we mention this? Okay, the elevation comes from an Amsterdam, so it's in fact a digital elevation model that comes from the Aster satellite and is downloaded from the River server from the NASA. And what else do we have here? There is a river. Do you see this? This is a river, this is the sea, this is the area where there is higher pumping, this is the area where there is less pumping, and this is the boundary, this is the limit of the boundary. Okay. On model, we are running with MODFLOW 2005. We tried this example with MODFLOW NWT, but there were some instabilities, so therefore we In our perspective, if you are dealing with higher differences in elevation, mud flow, and this solver is better. But if for these coastal aquifers where there is not much, or like you can assume that the layers are horizontal, MODFLOW 2005 is okay. On the packaging programs that we have used for this tutorial, okay, on the flow we are using LPF, and here is where you define the seawater intrusion. Okay, we have just one number of surface where the density is constant between surface. What does it mean? That you will have from here to the interface of the surface, you will have salt water, and from here to up you will have seawater. No, salt water, fresh water, seawater, fresh water. Yep. You can and the wells on this problem will pump fresh water till the, I mean, you have a well here, okay, and then this is the salt water seawater interface, and the well will be pumping fresh water till the seawater gets into the well, and the well then will be pumping salt water. And this is like very drastic, on my opinion, because you will have just two cases, whether it's you are pumping fresh water or you are pumping salt water. But it's easier to set up the model, so this is a tutorial model. And on reality you will have like the wells will be pumping on several stages. The wells will be pumping on several the wells will be pumping on and the salinity, or like the electrical conductivity, will increase as long as the with time. So I mean you won't have this case where you have fresh water and then you have salt water. You will have like a period where you will get higher increase on the hydraulic conductivity, on the the electrical conductivity or the salinity, and therefore like when dealing with this, a better conceptualization is the density varies linear between surface. However, do you know how the density varies? How is the density profile of your aquifer? Do you know it? No, I don't know it. So it's as well hard to define this, no? But if you are dealing with calibration with salinity, or like ion concentration, or like electrical conductivity, or solid TDS, and maybe you will need this one, who knows. Okay, then you don't have observations for this, and then on the solver, this is the solver of the saltwater intrusion, because there is there is the solver for the flow, and then there is the solver for the seawater intrusion. The solver for the flow is PCG as well, and this is the solver that solves just the distribution entre fresh water and salt water. Okay, and this is the zone 1 is the fresh water that has a dimensional density of 0, and the other one is the salt water that has a dimensional density of 0.025. So this is, I mean, the deviation of the salt water density from the actual fresh water density. Okay, cool. On the boundary conditions, we have recharge, that is the return. Recharge here is the return from irrigation. When there is irrigation, there is a excess of irrigation that goes back to the groundwater, or that goes to groundwater, and this is the recharge. It's it's not so easy to define. It's not so easy to understand, and it's not so easy to measure as well. And I hope that we can deal, or like we can get you can calibrate this recharge by you can calibrate this recharge by numerical modeling as well. And then we have the well package, that is the package that we are going to use for the pumping. We have the evapotranspiration. The evapotranspiration is the one that happens on the wetlands, because water that infiltrates into the aquifer will have a natural flow to the lower part, that is the seawater, and not all water will reach the seawater. Some part will stay here, and the water level will be closer to surface, and it will create some wetlands. So that's why we need this package, that is evapotranspiration. And then we have the general head boundary condition. Okay, the general head boundary condition is the one that we have used for the sea. Okay, I guess we can have whether constant head or general head. We have used general head, but because sometimes it's more stable since you use the conductance. No? And then we have the river package, because when we model ambient basins, the river, or like a stream network, is always losing water, so the groundwater discharges on the stream network. But in this case, we have water that comes from the river, and in this part the river will be losing water, so the groundwater will recharge from the river, and on this stage here close to the sea, the groundwater will discharge on the river. So that's why if you use the river package, the water can discharge, or the river could give water to the groundwater system. So it has the two options. Okay. What else? On the solver, this is the PCG. This is the one that deals with the groundwater flow, and we have with 100 iteration outer, 30 for the inner iteration. We don't use relaxation or damping factor here. Okay, cool. I guess my English is well enough that you are follow me up. If you can as well any commentaries of this kind of tutorial, or what can be done to make it better, like please let me know. Okay, then we are going to talk about the aquifer type and the hydraulic parameters. So we go to layer groups. Both aquifers, the upper and the lower, are convertible. That means that it can be whether those can be confined or whether those can be unconfined. So because when you are dealing with LPF, you have just convertible or confined or non-simulated. Remember that non-simulated is actually an aquifer that has only vertical flow, that the water cannot go into the plane of the aquifer, but whether perpendicular to the plane. Okay, cool. And the discretization, is just in one, so we have two layers. So this aquifer has just 2 layers. Then we are going to time. On the time, we have a steady state. We have a steady state of 100 years, and this steady state divided on 50 time steps. And remember, what will you need a steady state of 100 years divided in 50? Because the seawater intrusion package needs to follow the current number. So what does it mean? That it doesn't matter if your model is steady, like water cannot pass through, or like the time step has to be higher than the time required for a particle to get through one cell. I don't know if you follow me in this. I recommend you to read the paper of Seawater Intrusion package, because because I had many problems just because I have just set one time step. Okay, so this is a steady state of 100 years. We made this steady state in order to the aquifer to become on steady state. So we set up some arbitrary boundary initial conditions, and on 100 years the aquifer will have reached a steady state. No? So I think this is a good approach. And then the second stress period is 60 years of pumping. Okay, so we have 100 years of steady state and 60 years of pumping, and this 60 years is divided on 120 time steps. So what does it mean? That we are dealing with the aquifer we are simulating the aquifer every 6 months while pumping. And well, we use seconds. This is my main choice. We are dealing with groundwater model to use meters as longitudinal unit and seconds as time unit. Okay. Cool. What else do we need? What else do we need? Okay. On output control, no, output control is okay. Program options. On options, we need one more, that is continue running even if the solver closure criteria are not met. What does it mean? That in this on this tutorial, there are some wells that get dry, and there are some cells that do not fit the convergence, the closure criteria. But the balance in between the in and the out is always less than 1%, or even less than 0.5%. So, but if the simulation encounter just one time set where the solver closure criteria has not been met, it will stop. So with this condition, we say, okay, please, I assume the responsibility and go further from this. Okay. Okay. You say do not stop the model right there. Okay. What else do we need? Okay. Then we go to data, the data sets. Then we go to required hydrology. And then we say active. Well, everything is false because we have an object here that will be defined as true. So that's why the kx is 5 10 to the minus 5. This is the horizontal hydraulic conductivity, the same, and the vertical hydraulic conductivity is 10 times less. And this is why we wanted to have two layers, because we wanted somehow to assess this vertical anisotropy in order to define that water can go more into the direction, into more horizontally than vertically, and so therefore the lower parts of the aquifer will be less. The lower part of the aquifer will be less. The lower parts of the aquifer will contribute less to the groundwater flow, and that's why we want to. That's something that we want to to conceptualize on this model. Okay, the initial head is model top -2 because if you run it with model top at the beginning of the 100 years, you are saying that the model is completely saturated, and then that you will have evapotranspiration in your whole model, and it will bring you numerical instability because evapotranspiration will have huge value. No? Initial storage, specific storage, this is the most relevant, I think, is one. No, I think no. Maybe I'm wrong. This is 1.2 10 to the -5. Specific yield is 0.12. Okay. On the hydraulic parameters for a seawater intrusion, we have that the active surface elevation, so where we find the salt water at the beginning of the 100 years was at 80 meters below surface. That is for the whole aquifer, but however here on the sea is actually 0. The effective porosity is 0.1, and the source density flow zone, I mean, we are saying that if you are giving water to the system, is fresh water. As well, the sea, it has another boundary conditions. Okay, we say close. Yeah. Okay. Now we are going to look for the objects. Those are the wells that are located outside the area of influence, and these will have 0.0. These are pumping because the value is negative, 0.02 liters per second, and these ones are pumping 5 liters per second. Let me check once again. Yep. Okay. Those are the main. Let's look at the river because we want to see which are the hydraulic parameters for the river. The river is with the river package, and it's in the whole extension, and the river stage is model top -1. The conductance is direct on this value of 0.001, and the river bottom is 1 meter below. Okay, and then we have this. We have MODFLOW boundary element for the recharge and evapotranspiration. We take double click here, and appears this one. And this is the same object that defines the recharge, is the same as defines the evapotranspiration. And the evapotranspiration is 3 times. This is around 900 millimeters per year, I guess. Yeah. And the evapotranspiration depth, that is the routing depth, is 0.5 from surface. And the recharge is, we have 2 recharges here. Well, the first one is, I don't remember, is around 100. Maybe I'm wrong. Is 100 millimeters per year, while this is the 100 years of steady state, and on the 60 years of high groundwater exploitation of the aquifer, we have 150 millimeters per year, something like this. Okay, cool. Then we close this. Okay, and then we are going to see which is the general head that defines the sea. This goes to, this is located just on the first. Okay, then active surface elevation, I mean, it's saying that 0 is the elevation from the like the seawater elevation is at 0 here. So it's what is saying this is that what it's saying is that this boundary condition is defined waterhead, and as well this watershed is where is located the saltwater freshwater interface. Okay. Wow. Oh no, wait. This is not the one that defines. This one here is the one that defines the dataset 0. Yeah, it's located at 0. And the source flow density, this one is following the paper. If you set up this as -2 for the sea, fresh water can goes out from the system while salt water can get into the system. So that's why we have to define it as -2. Yep. And then on the general head boundary, you have from this to this on the boundary head of 0 and on the conductance of 0.02. Okay, so we have defined the whole setup. So the hydraulic conductivities, the model setup, the hydraulic conductivities, and the boundary conditions. What else do we need? Do we need something else than this? No. Actually, we don't need it. We go to model. We go to models. From model, we go to. Yep, we need it to run because we have talked about the main parts of the numerical model. So we run. We create a num. Please don't change those names, the full names but while giving some some courses, some people tend to change those names. Actually, I prefer that you rename the project. Yeah. Okay, the model is running extremely well. However, however, we have encountered many problems while dealing with this on numerical instabilities, on hydrological setup, and and that's why we don't want that you suffer from the same problems as I. So we have given this groundwater model that works, so you can learn a lot from what you can get from the model, and then like with this knowledge of what you can get from the model, and then you can deal with the numerical instabilities. Okay, so there are some time steps where you have not reached the closure criteria, but if you can see that the percent of discrepancy is really low, so we won't worry much about if this is a problem. Okay, cool. Yes. Okay, we are going to analyze two time steps. First one is at end of time step 50, the storage period 1, and this is the end of the 100 years of steady state. So, and this is the beginning of the groundwater exploitation. At the beginning, before that you pump on the aquifer, the river was, I will make this is on actually on cubic meters per second, and I will translate it in liters per second. So the river was given to the system, because actually this is in 35 liters per second, and the recharge was giving 133 liters per second. Those are the main inputs to the system. While on the output, the river was taking out 6 liters per second, and the evapotranspiration was giving out 51 liters per second, and the 110 liters per second went to the sea. And this is very interesting. Why it's very interesting? Because we have evapotranspiration 50 liters per second, and we have that the seawater is not giving anything to the system, and like seawater is like the sea is taking water out of the system. Okay, that's at the beginning. We have, at this time, we don't have any pumping well. Okay, then we go to the end of our pumping, of the 60 years of pumping, and we say storage, or like the depletion of the aquifer, is giving 20 liters per second. River is leaving 34 liters per second, and sea has become from taking out to giving water to the system 150 liters per second, and that's very important. And that is what makes the saltwater intrusion, because you have more water. I mean, because sea is giving water to the system. Recharge is 156. It has increased because the recharge rate have increased as well. Storage, there is some water that goes into the storage, but is minimum. The wells are pumping 370 liters per second, and there is no evapotranspiration. All the wetlands that you have on this aquifer have gone, and as well there is no water that goes, I mean, like all water goes into the system. No, the sea give waters to the system, but the system do not, or the aquifer system do not give water to the sea. Okay, cool, that's very cool. Okay, what else? We are going to see how is the final stage of we are going to import the water heads to see how is the stage at the beginning of pumping. So it's this one, and at the end of pumping, this one. Okay, at the beginning and at the end, and we are saying complete. By default, it will represent what is the end. Okay, at the end of the 60 years of precipitation, and I can do some like chiefs, so look, it's more pedagogy. Yep. And so I will show this is at the beginning. At the beginning, you will have this distribution of the groundwater cells on the first layer. On the second layer, there is a depletion of the this is at the beginning of the pump, at the beginning of pumping, for the first and for the second. But look, for this is for the first, and this is what ends up after 60 years of pumping. We have a whole distribution, like we have a depletion, like many cells that were actually active when dry. And here we have, this is the impact of pumping, and I don't know if you see here, like it appears the water table is -16, -15, -16, 15, no? So this is actually the water table that was supposed to be above sea level, but actually it has decreased. Okay, cool. Now we are going to import the seawater interfaces, that is this ZTA, and this is 50 and 150. Neither, these ones are neither. Okay, and now what I am going to do, oh sorry, yeah, cancel. I will do it again because I have some data on my model, but in this time data, delete model results. I will import, I have some data, and model news store one data after the other, but I don't want to make confusion, so I import it again. I delete all my model results and then import it again because I really want to. I'm importing the water heads again, but in this time I say neither because I want to import it, but I don't want to represent it. And then again I will go the CTA. Okay, cool. And what we are going to do now is we are going to just analyze this green stripe that is a cross section, but we are going to analyze it on the here, because we want to see these are the pumping. Maybe I exaggerate. Yeah. These are the pumping wells, and this is C, and then we are going to see which was the initial water table and which is the after the 60 years water table. So data visualization, cross sections, data sets, optional, model results, water table. The first one is at 50. At 50 we are going to represent it by the green color, and at the end of the 60 years, this is at the beginning is green color, and at the end of the 60 years is blue color. Close. And then here we see which is the impact. At the beginning we have this water table, and due to the heavy pump intensity, we have decreased the water table on 26 meters. Okay. However, now we are going to see which is the actual seawater saltwater interface and the original saltwater seawater interface. Okay, so we go to see data visualization on data sets, optional, model results, 3D data. We have, this is the initial and this is the actual, and the initial is as well green, and on the actual is blue. And if you see, this is the original saltwater intrusion, and this is the actual. Maybe I will, since those ones are, I will put it as pink. Yeah. So what does it mean? That all these wells will be pumping just salt water. that means that. So if we go to another cross section as well, we have here that all these wells are pumping salt water, and this well is pumping fresh water, while these wells are well as pumping fresh water. Okay, and here as well we have that these 4 wells are pumping fresh water, while this well is pumping already salt water. And this situation happens for example here, just this well is pumping fresh water, so water quality has been affected on these wells. Okay, and this is mostly this tutorial. I hope that this tutorial have been of much benefit for you, and we will post more tutorials. This is quite complex tutorial. From my perspective, we could have done it lighter, but the topic is very interesting, and this is a topic that is really an issue for many places. For the groundwater, is an issue for places with high groundwater extraction on coastal aquifers. Please follow us on Facebook Hatari Water, Twitter Hatari Water, and if you see this post share it on your social networks. Please sign up for this groundwater, for this YouTube video. All the files related to this tutorial are located on the description of the video, and I hope that we can get more tutorials, and then we can do some webinars as well. So if I have already gave my this is my email, so if you have an idea or whatever we can do in order to diffuse, to make, we really work on making open source software and water resources more available and more understandable, and especially on groundwater model use and its stack, because it's my expertise as well. We will be happy to make these initiatives as well. Okay, my name is Saul Montoya, and thank you for your patience, and I hope that you have liked this video. Okay, see you. Have a nice day. Bye bye.